Okay, we start chapter 5, which is majorly gonna discuss the different types of isomers. Isomers will have the same chemical formula, a different structure drawing. But for this chapter, we'll introduce the R and S system of isomerism. We will define enantiomers. We will define diastereomers. These are keywords you have to know. We will define diastereomers and mesocompounds. So how can you tell these types of isomers apart? How can you tell them apart? Enantiomers, diastereomers, mesocompounds. You'll have to use RNS system. Here you're looking at a structure. It looks very complex. The red balls are just oxygens, the white ones are hydrogens, and the black one is carbon. The stretches are just bonds. So it looks very complex, but it's a small one. So usually one will want to identify all the carbons that is connected to 4 different groups or 4 different elements. That carbon that's connected to 4 different groups of or elements is going to be termed as chiral. So the other key term we will discuss is chirality. Okay, so make sure you are comfortable with these terms: enantiomers, diastereomers, mesocompounds, and chirality. Okay, so let's talk about stereochemistry. What's stereochemistry? That's gonna be covered in this chapter. It's the key point of this chapter. Stereochemistry is the study of 3D aspects of molecules. So stereoisomers are molecules that are only different in 3D arrangement of their atoms. The stereoisomers must possess one or more chiral centers. Remember, I said chiral center is where, for example, in a carbon, you should have 4 different groups attached to the carbon for the carbon to be qualified as chiral center. Okay, so there should be no mirror image, and they should not be superposible. Okay, so for example, if you hold your hand and you match it to the other one, right, both of them facing the same side, you see the thumb is not overlapping unless I rotate my hand, and now the thumbs can overlap. So my pair of hands are chiral because they cannot superimpose. They cannot overlap unless I do a rotation of the palm. So you have your hands, as use it as a cheat sheet. You'll know what superimposable means. Okay, they should match without rotation. So optical activity relates to a molecule's ability to interact with polarized light in an instrument. So if the polarized light is turned right side, then it's called dextrorotatory, or left side is called levorotatory. But I want to tell you that in your book or in the PowerPoint, don't worry about optical resolution. So you don't need to worry about how the polarimeter is used, because this is a virtual class. If it were in face-to-face interaction, I would have explained to you well using the instrument. So don't worry about optical activity and polarimeter and the specific rotation stuff. Don't worry about that. All I want you to know is that when a molecule is chiral, it's gonna be optically active. Okay, when a molecule is chiral, which means there's no internal plane of symmetry, but you also, at the same time, you also have chiral carbons, then the molecule will be optically active. And the polarized light will be rotated either to the right or to the left. That's all I need you to know. And this is the rotation angles specific for these drugs or hormones: epinephrine, testosterone, morphine, sucrose, cholesterol, ceftoxin, residotamidine, glutamate. So we can determine their purity based on their rotation. But like I said, I'm not going to emphasize on specific rotation. I'm not going to emphasize on the optical activity or how the instrument works. My goal is to discuss the molecules and define enantiomers, stereoisomers, and mesocompounds. So, what is chirality? All right. So consider an object. For example, a chair. It's either going to be chiral or achiral. Now, if you look at this chair, you can cut it into equal half from top to bottom, right? If you place it in front of a mirror, the image too can be cut into equal half. If I take a half from here and a half from here, I'm going to get that chair. So this chair right here is achiral. The reason being, it can be cut into equal half and it's super possible. You remember, for example, when you have a function at home where you can stack chairs one on top of the other very well, then you can carry them very well, because you can stack this chair onto that or stack chairs like this onto other chairs, then those chairs of this form will be superposible. They can stack together. But now for this one right here, it's impossible because now you have a desktop. It's so hard for you to cut this molecule into equal half. Then this chair and its image are not superposible. They are non-superposible. And for that case, this chair and its mirror image are said to be chiral. Like I said, your pair of hands are chiral because you cannot overlay your thumb of the left hand to the right hand. Unless you do a 180 degrees, then they will be superposible. That's the definition of enantiomers. Enantiomers are superposible mirror images of compounds. Okay? And they should not have internal plane of symmetry. So like here, there is no internal plane of symmetry, meaning you cannot cut it into equal half. No internal plane of symmetry. Cannot cut it into equal half. So this chair and the mirror image are not superposible, they are chiral. This one and the mirror image are superposible because you have an internal plane of symmetry. And basically that's what chirality simply means, but we'll make it complex soon. An achiral object is one that is not chiral. So chiral, achiral. So whenever you introduce the achiral, it means it's not. It's the negative. So an achiral object will have an internal plane of symmetry and a mirror image, and its mirror image, of course, will have half the image of the other one. So just like a cup can be cut into equal halves, which means if this side is the original, then the mirror image is the same as the original. Your hand, on the other hand, cannot be cut into equal half. Can you cut your hand into equal half? No, because now the thumb which is on the outside of the mirror, on the front of the mirror, is not at the back. Instead, you have a pinky. So you cannot cut your hand into equal half because the thumb is not the same as the pinky. So this cup right here is achiral because it contains an internal plane of symmetry. One half of the mirror image is the same as the other one, so it's achiral, just like this statement is saying. Here, your palm is chiral because again, you cannot cut it to equal half. Okay, excuse the typo there of the spelling. This should be achiral. So we've given the overview. Now let's look at molecules. Okay, for molecules, a chiral center is an sp3 hybridized carbon atom with 4 different groups, and those groups could be groups of atoms or just an atom. If 2 or more groups are identical, then the molecule will possess plane of symmetry and it's gonna be called achiral. Okay, so for example, looking at this molecule right here, should have been drawn like this. I'm just gonna show the hydrogens for purposes of clarity, but really I should not show those hydrogens. Now our focus is the central carbon. Does the central carbon have 4 different groups or atoms? The answer is no, because I see a methyl and a methyl. I should remind you that the atom of an element is spherical. Chlorine is bigger than hydrogen, so you consider chlorine to be a basketball and the hydrogen to be what will it be? A marble or an M&M. Something small and spherical. Let's say a tennis ball. So tennis ball, basketball, then the carbon, take it to be an orange. Okay. So you can really cut the molecule into equal halves because those bonds are like straws that you can cut into equal half, and you see that this CH3 is reflected to the back if this plane of symmetry is your mirror, like this mirror right here. So this same molecule is what you have on here. You're shown that the mirror can cut it into equal half. There's internal plane of symmetry, then the entire molecule must be achiral. Okay, so this molecule is achiral because there's at least 2 groups that are similar. If 2 or more groups are identical, then the molecule possesses an internal plane of symmetry and it's going to be labeled achiral. Now, what about what we have here? So this time we have a carbon, we have a chlorine, we have a CH3, we have an ethyl, ethyl is CH2, CH3, and then we have what? A hydrogen. I'm gonna pick a different color pen so I can circle things. So chlorine is different from hydrogen. Chlorine is different from CH3 and the ethyl. Hydrogen is different from all these other groups attached to the central carbon in question. So this carbon right here contains or is surrounded by 4 different groups of atoms or 4 different atoms. So in that case, this carbon is said to be chiral center. Now notice that the whole molecule does not have an internal plane of symmetry, so the whole molecule is going to be called chiral. Because if you try to cut the molecule into equal half, there's no way you're gonna have a reflection on the backside of the same molecule. Okay, is that okay? Is that okay? All right, now if you come back here, if you want to check if they superimpose, it's very simple. Place the molecule in front of the mirror. Whatever you see in the mirror must match or overlap with the exact placement of the groups. So like you see how the hydrogen is for the original molecule, which is this molecule. If you bring them very close, the hydrogen matches with the hydrogen of the mirror image. The CH3 matches the CH3, the carbon matches the carbon, the hydrogen matches the hydrogen, chlorine, metal. So everything is matching without much complications. So, but if you try to do the same thing here, there's not gonna be a perfect matching. Unless you rotate the molecule, then it will match. Now this is not gonna show you very well, so I'm gonna use a simulation. So let's suppose we are matching this element, these two molecules. You see how the black carbon has 4 different groups? So let's try and bring the second molecule to see if they're gonna match. You see the color codes are different. You have the orange, the green, the orange. So if you bring this one down to try to match it, they obviously are not matching. Can you see that? The green and the orange, they cannot match. So molecules that possess 4 different groups around a specific carbon, and they don't have internal plane of symmetry, like this guy does not have internal plane of symmetry, it's the same molecule. Those molecules are said to be enantiomers. So they have chiral centers, which means they at least have a carbon with 4 different groups around it, and there's no internal plane of symmetry. So that's enantiomer. Now, on the other hand, if you have at least 2 groups that are the same, and you replicate the molecule such that you have 2 of them which are similar, and then drop it up or down, you'll find that they are matching. See how it looks like it's the same molecule after the overlap? So these ones are superimposable because they can well match when you bring them together. All right, so, and that happens because you at least have 2 groups which are the same, and also the molecule has internal plane of symmetry. I can cut it through this plane, everything into equal half, and then the metal on the left will be reflected to the metal on the right. So these 2 molecules are identical. You can easily match them. You can easily superimpose them. But if you try to do that for enantiomers, which by definition I said they are mirror images of the same molecule that don't have internal plane of symmetry, if you try to do that, there is no match. You see the green and the orange are not matching at all. So that's what we are trying to explain on this busy slide. Okay, so let's move on. Very soon we'll talk about RNS, and it's gonna be easier for you to define enantiomers and diastereomers and meso compounds. Molecules which are non-superimposable mirror images, because they have chiral or stereogenic center, are called enantiomers. So I'm gonna insist there should be no internal plane of symmetry. This is very important. No internal plane No internal plane of symmetry. Okay? No internal plane of symmetry. Now, first, let's determine if we have chiral center. Do we have chiral center on this molecule? What is chiral center? Again, you're looking for 4 different groups or atoms on a carbon center. That's what you're looking for. So, is this carbon here chiral center? The answer is no, because you have 3 hydrogens. Of course, they are the same. We said you don't want 2 groups that are the same. Here you have 3 that are the same. Is this one chiral center? The answer is no, because again, it's not sp3, it's sp2. So we are left with this one right here. I'm going to mark it with an asterisk. That's chiral center because you have a hydrogen, an OH, a CH3, and a carboxyl group. So that's chiral. Place this whole molecule in front of a mirror. We should see this as the image. Okay? We should see that as the image. Next, rotate 60 degrees. Rotate 60 degrees. So 60 degrees, let's see. If we rotate it 60 degrees, who will be where? I think you're rotating across this hydrogen 60 degrees. Then that will mean this will go here. Yeah, so this will go here. And then this group will go here. And this will go on the other side. So you end up with this molecule. Okay. And then, so now compare this to that. The only difference you have between this molecule and this molecule is the orientation of OH and CH3. Here OH is towards you. Remember what we said in, I think, chapter 1. This means towards you. And then here the OH is away. That's the only difference. Okay. So there's no way you're gonna superimpose these 2 molecules. They are enantiomers. Okay. I don't want you to stress yourself with all these rotations unless you have the model kit where you can build a molecule and visually look at it. We will want to define RNS, which will help us to do that. So again, remember, enantiomers are non-superimposable mirror images. They are identical, and they have let me see what to say here. They have different chiral properties, and therefore will do their rotations differently. And like I said, we don't want to care about the polarimeter, so I'm not going to emphasize on that point. Just know they're different. The reason why you will want to learn about chirality is because of enzymes. Enzymes are chiral. You know, the enzymes operate on lock and key. You can't use your key to come open my door. It's very specific. So you'll see that the R configuration of an enzyme will be preferred by the receptor of whatever the enzyme catalyzes, or will be preferred by the substrate. So enzymes are specific in nature, and biological enzymes are usually chiral, and that's why we are learning this. It's because of their RNS configurations. Okay. So enantiomers will have different chiral properties and therefore different activity even in biological processes. I don't know if you've ever heard of drugs called placebos, where you have a drug that is inactive and the other one is active, even though they have the same structure. That's what you're trying to talk about here. So now, before we define RNS and go to complexities that I was trying to imply here, we want to make sure that you understand chirality. So is this molecule chiral or not? Remember, chiral, you are looking for 4 different groups around the central arrow. So does the carbon here have 4 different groups? No, it has 2 and 2 sets which are the same. In fact, I can have an internal plane of symmetry. Answer here is not chiral. What about this one? Still, those are the same. So that carbon is a chiral. The molecule becomes a chiral. So if it's not chiral, it's called achiral. What about this one? The carbon in the middle has 4 different groups. This one is chiral. What about this one? I see bromine, methyl, hydrogen, methyl. This has 4 different groups. It's chiral. And then here, there's a problem. 2 metals sharing the same carbon. Achiral. All these carbons have at least 2 groups or atoms that are the same. Definitely the hydrogens are the same sitting on those carbons. So all those are achiral. But when we get here, I have 1, 2, 3, 4. So I have 4 carbons to the left. And then I have 1, 2, 3, 4, 5. 5 carbons to the right. So 4 carbons, 5 carbons, 2 different groups. I have bromine and hydrogen. So the carbon in the middle here has 4 different groups: H, Br, pento, butyl, and the bromine. So this entire molecule is chiral. There's no plane of symmetry. Definitely on the right you have a double bond. Here you don't. So these 2 carbon chains are different. You have Br and H. So this carbon has 4 different groups, which makes this entire molecule chiral because there's no internal plane of symmetry. So you have to have 4 different groups. You don't want plane of symmetry. No internal plane of symmetry. You don't want the plane of symmetry. At the same time, you want 4 different groups on at least 1 carbon. Shown here is an example of a drug, L-DOPA, the L version, the R version. So the L version is the one that's active because it fits perfectly on the enzyme where it activates the cascade of mechanisms that helps to increase the dopamine concentration in patients, for example in patients with Parkinson's disease, to reduce their shaky effect. It just helps for easy blood flow, especially for patients with low blood pressure and all that. So anyway, the molecule L-DOPA is more active than, or it's active than the one that is D, the D version. So D-DOPA will not work. So L and D just refers to the optical activity, rotation, that I did not go into. But again, we'll come back and explain the R and S configuration and say which one is more active, the R or the S. So remember, enzymes are specific in nature, like lock and key hypothesis. So if you have the wrong stereochemistry of the drug, it's not gonna activate some of the biological reactions in your body. So it's very important to have the right stereochemistry in a drug. That's why again we're learning about enantiomers and all this stereochemistry. Now, atoms that are related to one another by a mirror plane are chemically equivalent and have the same chemical properties. In fact, for hydrogens, if hydrogens have the same neighbors, for example here, same neighbors, those hydrogens are said to be homotopic. They're one and the same. But here, these two hydrogens have different neighbors, you see. The hydrogen to the left is neighbored by an ethyl, the hydrogen to the right is neighbored by a methyl. So those are called enantiotopic hydrogens. So it's important to know what chemical equivalence means. Chemical equivalence means relates to the neighboring groups. Do you have the same neighbors or not? Okay. So now, let's now dig into RNA system, and then we'll go back and explain which L-DOPA is useful. Okay, now here we use RNase nomenclature to find isomerism and distinguish between two compounds and define whether they are RNS. So we do so by assigning priorities. So we assign priorities of the groups based on atomic number. Okay, so assign priority based on atomic numbers in the periodic table. So this rule is called Kern-Ingold rule. So we'll assign numbers 1, 2, 3, 4, and then before you assign RNS, the fourth group must always be away with a dash bond. And the 1, 2, and 3 will be considered to decide whether you're going, let's say, clockwise, which will be the R, or counterclockwise. For example, counterclockwise, which would be the S. So that's the overview, but we'll have to do it to see it well. All right. So okay, so it's either you're looking at it this way, the molecule, where now you have group 1, 2, 3. So 1, 2, 3, you're going clockwise, that will be an R. Or you're looking at it this way, where this group 1 will be here, group 2 will be here, group 3 will be here relative to where you're standing. So you have 1, 2, 3. You're going counterclockwise, that's an S. So R is used because it came, I think, from a Greek word rectus, and then S is sinister. Counterclockwise, clockwise. D is the fourth group. It must be away from where you are looking. So you see how it's away from the eye. It's away from the eye. So before you assign RNS, always make sure that your smallest group, group number 4, is away from you. I repeat, before you assign RNS, your final answer is RNS, always make sure group 4 is away from you. So again, we'll use atomic numbers to rank and assign priorities 1 through 4. Okay, so use atomic numbers according to Kern-Ingold rule. Then compare, if there's a tie, then you have to move one more step. So for example, let's say you have group A, B, and then you have a CH3, and you have a CH2, CH3. Now, if this is what you want to assign as RNS, then you have a carbon and a carbon, you can't decide. But moving forward here, you'll get a hydrogen, right? If you have to move forward, either direction you go, you'll always meet a hydrogen. Here, if you move forward, you meet a carbon. So that makes the ethyl win. So you always have to compare the next atom of the chain to find the tiebreaker. If there are multiple bonds, pretend that that element, for example, this carbon right here, pretend that it's bonded to 3 other elements where it's bonded to. So it's treated, this carbon right here is treated as it's bonded to 3 other carbons. This one too will be treated as if it's bonded to 3 other carbons. Alright, if it's this one, it's gonna be treated as if it's bonded to 2 oxygens because it's doubly bonded to an oxygen. Okay, see how it's treated as if it's bonded to 2 oxygens. Alright, so those are the 3 common rules. Now let's try and assign priorities and then assign RNS. I will emphasize that it's always a good idea to show your carbonyl. Let's take out one of the oxygens and put it as a carbonyl. So I see I have a hydrogen, okay, and then I have the nitrogen and carboxyl group. So according to the periodic table, hydrogen will have the least atomic number. So we give it a 4. If you want, give it a D. Okay, because you're going A, B, C, D. If you want to use alphabets to rank, or you're going 1, 2, 3, 4. So D is 4. And then this is a CH3. So there's a carbon and a carbon we can't define yet. But we know that nitrogen has atomic number 7. So that's going to take priority 1. So that's an A. Okay. Now between the carbon to the doubly bonded to the oxygen and the carbon bonded to hydrogen, obviously the one bonded to the oxygen will win, because carbon and carbon, there's a tie, atomic number 6. We move one step forward, you get oxygen. So this carbon right here is bonded. In fact, let's do it. That carbon is bonded to, we pretend it's bonded to 2 oxygens with the double and the one other oxygen, so 3 oxygens. And then this carbon right here is bonded to 3 hydrogens. Obviously there's a tiebreaker because oxygen has higher atomic number than hydrogen, so this carbon gets number 2 because you already assigned nitrogen 1, and then this will be number 3. Now the rule is the smallest group should be away from you. So if this is here, then your I should be somewhere here. Okay, your I should be here to make sure that the 4th group is away from you. Now focus on number 1, 2, and 3. So we should write them like this: 3, 2, and 1. That's what you should be seeing standing this side. 1, 2, 3. So you're going counterclockwise. So this carbon here in the middle has a chirality of S. That's what we are looking for. Okay. We kept our small group away. We assigned elements directly bonded to the chiral carbon. We assigned the priorities based on atomic number. So now here again, hydrogen will get number 4, so which means my I should be here because the smallest group must be away for me. So this is number 4, alternatively call it D. Now, which is the carbon I'm looking at? I'm trying to assign chirality of this carbon because I see it's bonded to 4 different groups. The carbon is bonded to a hydrogen, it's bonded to an isopropyl, right, which is this part. It's also bonded to an ethyl, and it's bonded to, the carbon is bonded to a tert butyl group. So the carbon in the middle is chiral. center. This is a chiral center, so it qualifies to be assigned RNS. So let's do that. So now there's a problem. I see a carbon here, which is having 2 hydrogens. There's a carbon here, there's a carbon there, so there's a problem. So we have to follow the tiebreaker thing. So let's go with this carbon. Moving forward, this carbon is bonded to 3 other carbon. This carbon right here is bonded to carbon 1, 2, 3. So let's list 1, 2, 3. Okay. Moving forward, you'll find it's bonded to 3 other carbons. So let's do the same for this carbon here. So moving forward, this carbon is bonded to a carbon which happens to be a CH3. It's also bonded to 2 hydrogens. So I'll write the carbon first, then the 2 hydrogens in decreasing atomic number. We are trying to look for which carbon should win, and then where's green. Okay, so next, this one. So for this one, moving forward, it happens to be the isopropyl, right? So this carbon right here is bonded to 2 carbons and a hydrogen. So I'll write the 2 carbons moving forward, then the hydrogen. Now, which one do you think wins? The ones in red, in gray, or in green? Of course, the ones in red, because if you sum up the atomic numbers, 666, you get 18. Here you sum up C611, you get 8. 661, you get 13. So this one right here, this carbon will get priority 1. Okay, that one will be priority 1. So let's give it a 1, and then followed by this one in green, because again that carbon will win over this hydrogen. Okay, here this carbon won over the green hydrogen. That's why this one won. Okay, see, the tiebreaker is right there. Obviously, the second carbon is winning over this hydrogen anyway. So this priority 1, it's all carbons bonded moving forward from this carbon, and then this will be priority 2, and then the ethyl will be priority 3. Using eyeball, you just look at which carbon is more substituted, which carbon lacks hydrogens. That's how you know which gets high priority, which is this, then this, then this. Now if you're standing here, your numbers 1, 2, 3 can be written as 1. I have my 2 almost to my left, and then I have my 3. So I'm going counterclockwise. The smallest group, number 4, is away from me. I don't need to write it here on my circle. So it's an S. So this carbon right here in the middle has S configuration. You see, you have to practice. You really have to practice. This carbon right here is not chiral carbon. This is not chiral carbon, because you have 2 groups that are the same. This is not a carbon, that's part of formula of Cl. But now if you come here, this carbon right here is chiral, because it's bonded to 4 different groups: chlorine, hydrogen, this tail, and the butyl group. Now chlorine will win. It has atomic number of 17, and then hydrogen will be the babiest. So the question is between this carbon, okay, remember that carbon, if we branch it, is a butyl group. Between that carbon and this chain, who gets priority? Now we'll have to rank what's bonded on immediately on this carbon in that column, because carbon and carbon we can't tell, they are the same. So now we look at groups bonded to these two carbons moving forward. So for this carbon moving forward, I have, it's a tert-butyl, so I have 3 carbons if you draw the open structure. But for the other one, so for this one, for this carbon right here in blue, moving forward, it's bonded to a carbon and it's bonded to 2 hydrogens. So carbon, 2 hydrogens. So again, you get a tiebreaker. This carbon has atomic number 6, hydrogen 1. So this whole red group wins. This tert-butyl group wins. So it gets number 2. And now this will be number 3. This carbon right here will be number 3. Assigning priorities around the chiral carbon. So question is, where are we standing? We are standing in the position, same position as you're looking at your screen right now, because this hydrogen, it's already at the back, so we cannot draw our eye here, here, or to the back. We're already looking at it the right way. The hydrogen is already at the back. How do I know that? The bond is broken, the chlorine is towards us. We want the 4th group at the back, right? So if I'm to write my numbers, I'll have 1, 2, 3. Okay, so 1, 2, 3. So we are going 1, 2, 3, and that's counterclockwise. That's an S. So again, this carbon in the middle is an S. None of this carbon is chiral except this one right here. I'm going to mark it with an asterisk. Sulfur atomic number will be higher. 1 hydrogen will have the least atomic number, so give it group 4. So you can call this D, call this A. You can use alphabets A, B, C, D, or numbers 1, 2, 3, 4. So now this one is bonded to 3 hydrogens. This one is bonded to 2 hydrogens to make 4 bonds around the carbon. We already discussed how to know that, which means that this one right here is more substituted than this, so this will get 2. Otherwise, you can draw arrows and rank to find the tiebreaker. Then the CH3 will be 3. So my numbers are looking funny. So hydrogen is drawn on top. So the only way we will make sure hydrogen is away from us is our eye being down here. That's the only way our group 4 will be away. So the rule is the 4th group has to be away. The rule is the 4th group has to be away before you assign the true assignment. That's why I'm putting my eye below the molecule to make sure the hydrogen is away from the eye, from this eye orientation. So if the eye is here, then the numbers will look like this. 1, 2, 3. So this time we are going R. Let's see, is that true? No, that's not true. We should be the other way around. One should be on top, 2 should be at the bottom. So this is what you'll see: 2, 3, 3 to the right, 2 to the left, and 1 somewhere here. So this is what you should see: 1 on top, 2 should be to the left. You see how it's away with the dash bond, and then 3 should be to the right. So again, you're getting S. All right, so if I'm to assign the chirality on this carbon here, oxygen will be atomic 6, so atomic 8, so it gets priority 1, hydrogen gets priority 4, And then this carbon has 2 hydrogens, so it's least substituted. Okay, so we'll give it a 3. And then this carbon here will give it a 2 because it's bonded to an oxygen over this, which is bonded to hydrogen. So if I am to assign the chirality, so I have 1, 2, 3. Okay, so the answer here will be an S, but there's a problem because the hydrogen is pointing towards us. It needed to be away. Because it's a ring, we can't really rotate it. So instead of saying that this carbon right here is an S, we'll say it's an R because hydrogen is towards us. The rule is the smallest group must be away. When the smallest group is towards us, the assignment is S, right? Counterclockwise. But we want it to be away, so the true assignment is R. Now, going back to L-Dopa, let's assign RNS. So hydrogen will get priority 4, is the babiest. Of course, nitrogen will win because it has a high atomic number around this carbon, so it gets 1. And then this carbon has a carbonyl, or it's bonded to 2 oxygens, but this one is bonded to hydrogens. So by eyeball, I know this will be priority 2 and this will be 3. Now, hydrogen is already away, so probably our eye is looking the way we're looking at our screen right now, at our monitor, so the numbers stay the way they are. So we are going, following the numbers, we are going S. So this center here is an S chirality. Here, our eye should be from this side, because again, hydrogen's on the plane and it's at the back. And then nitrogen will be still 1, this carbon will be 2, this will be 3, so you're going 1, 2, 3. Okay, so the fourth group is at the back already. So here we are going R. So you see the chirality of this carbon is R. So there's no internal plane of symmetry. The chirality has switched from R to S. So the relationship between these two guys is enantiomers. Enantiomers will be mirror images. So if this is S, that's R. If this were to be R, this would be S. That defines enantiomers. Let's practice some more. So let's say you are given this molecule. And you're given okay, how to modify it. So the question is, are they same or enantiomers? Now that you know what enantiomers are. So obviously we have a carbon that's chiral. It has 4 different groups there and there. So we need to assign chirality before we determine whether they're enantiomers or not. So oxygen gets priority 1, hydrogen priority 4. Obviously here it's CH2, which means this carbon is more substituted than the CH3. So this gets 2, this gets 3. Otherwise you can find the tiebreaker the long way. So because hydrogen is on top, our eye should be down here, which means the numbers, looking at the molecule this way to keep our group away, the numbers will be 1 on top, I think 2, let's see who will be on top. I'm trying to see who will be on top looking at the molecule that way. 2 will be on top, 3 should be here, and 1 should be here, because 3, usually with the dashboard, that's away or to the left. This should be to the right because it's shaded. So we are going S for this one. And then for this molecule, we still have to look from the bottom because we really have to keep, by rule, our fourth group should be away from us. That should be 1, 2, 3. So again, 2 is at the top, 1 should be on our left, 3 should be on our right, and we are going R. So these two molecules are enantiomers. Okay, they are mirror images, just based on chirality, S and R. You see, you have the same groups. Turns out you assign chirality. One is this center is an S, this chiral carbon center is an R. They are opposite, so it's enantiomers. There is no internal plane of symmetry. So again, you'll have opposite stereochemistry for internals. You'll have opposite stereochemistry, and then there will be no internal plane of symmetry. No plane of symmetry. Okay.